are a truth table for the control unit. It will be useful to try to define the control function informally because the setting of the control lines depends only on the opcode. So each control signal should be 0, 1 or don't care for each of the opcode values. This simple data path and the control unit figure the input to the control unit is the 11-bit opcode field from the instruction. The output of the control unit consists of three 1-bit signals that are used to control multiplexers are REG to LOC, ALU, SRC and MEM to REG. Similarly, three signals for controlling read and write in the register file and data memories are REG write, MEM read and MEM write. Also a 1-bit signal used in determining whether to possibly branch and a 2-bit control signal for the ALU operation and AND gate is used to combine the branch control signal and the zero output from the ALU. The AND gate output controls the selection of the next PC. Notice that PCSRC is now a derived signal rather than one coming directly from the control unit. This table defines how the control signal should be set for each opcode. This information follows from the previous figure, which is simple data path with the control unit. The first row of the table corresponds to the R format instructions, which are add, subtract, and OR instructions. For all these instructions, the source register fields are RN and RM, and the destination register field is RD. This defines how the signal ALU, SRC, and REG to LOC are set. Furthermore, an R-type instruction writes a register REG write is equal to 1, but neither reads nor writes data memory. When the branch control signal is 0, the PC is unconditionally replaced with PC plus 4. Otherwise, the PC is replaced by the branch target if the 0 output of the ALU is also high. The ALU OP field for R-type instructions is set to 10 to indicate that the ALU control should be generated from the opcode field. The second and third row of this table gives the control signal setting for load and store instructions. These ALU, SRC and ALU OP fields are set to perform the address calculation. The memory read and memory write are set to perform the memory access. Finally, REG to LOC and REG write are set for a load to cause the result to be stored in the RT register. The ALU OP field for branch is set for a pass input B, which means ALU control is equal to 0, 1, which is used to test for 0. So notice that the memory to REG field is irrelevant when the REG write signal is 0. Since the register is not being written, the value of the data on the register data write port is not used, so the entry memory to REG is the last two rows of the table is replaced with X, means don't care. A don't care can also be added to REG to LOC for load instruction which does not use a second register. This type of don't care must be added by the designer since it depends on knowledge of how the data path works. Now we see how each instruction uses the data path. This figure shows the flow. These figures in upcoming slides shows the flow of three different instruction classes through the data path. The asserted control signal and active data path elements are highlighted in each of these slides. A multiplexer whose control is 0 has a definite action even if its control line is not highlighted. Multiple bit control signal are highlighted if any constituent signal is asserted. Now we start with the operation of the R-type instructions. So this figure shows the operation of the data path for an R-type instruction such as add x1, x2, x3. The four steps to execute the instructions by the flow of information is as given. Number one, first of all, the instruction is fetched and the program counter is incremented. Number two, the register X2 and X3 are read from the register file. Also, the main control unit computes the setting of the control lines during the setup. Number three, the ALU operates on the data read from the register file using portions of the opcode to generate the ALU function. In the last, the result from the ALU is written into destination register X1 in the register file. Similarly, we can illustrate the execution of a load register such as LDUR X1, into X2, offset. The 5 steps to execute this instruction is as step 1, an instruction is fetched from the instruction memory and the PC is incremented. Number 2, a register X2 value is read from the register file. Number 3, the ALU computes the sum of the value read from the register file and the 6 extended 9-bit of the instruction offset. Number 4, the sum from the ALU is used as the address of the data memory. Number 5, the data from the memory unit is written into the register file, which one is X1. So this figure shows the control lines, data path units, and connection that are active are highlighted. As Similarly to the store load instruction, a store instruction would operate very similarly. The main difference would be that the memory control would indicate a write rather than a read signal. The second register value read would be used for the data to store, and the operation of write the data memory value to the register file would not occur. Finally, we have the operation of the compare and branch R0 instruction, such as CBZ x1, offset. In the same fashion, it operates much like the an OR format instruction, but the ALU output is used to determine whether the PC is written with the PC plus 4 or the branch target address. The four steps in executions are as number one, an instruction is fetched from the instruction memory and the program counter is incremented. The register X1 is read from the register file using bits 0 to 4 for the instruction RT. The ALU passes the data value read from the register file. The value of PC is added to the sign extended 19-bit of the instructions offset are shifted left by 2. The result is the branch target address. The zero status information from the ALU is used to decide which adder result to store in the PC. The control lines, data path unit, and connections that are active are highlighted in this figure. After using the register file and ALU to perform the compare, the zero output is used to select the next program counter from between the two candidates. Now we have seen that R format, load, store, and CBG instructions operates in steps. So let's continue with the control implementation. The control function can be defined by this following figure. This figure defines the logic in the control unit as one large truth table that combines all the outputs and that use the opcode bit as input. When we convert instruction into its binary format, then we see that its opcode field is encoded into 11 bits or 6 bits. When it is encoded in 11 bits, it has bit number 21 to 31, and when it is encoded in 6 bit, then it is between 26 to 31 bits. So the top half of the table gives the combination of input signal that correspond to the 4 instruction class, one per column, that determines the control output settings. The bottom portion of the table gives the output for each of the 4 opcodes. Thus, the output REG write is asserted for two different combination of inputs. We simplify the truth table by using don't cares in the input portion to combine the four R format instructions together in one column. We would have instead replaced that signal column with 4 column for the instruction add sub and or. The output would have been the same for all 4 of these are format instructions. So we see that when we convert an R format instruction into its binary form, then from bit 21 to 31 it shows the opcode field. So we have 1 XX0 1 0 1 XX0 0 0 bits common for all the four operations that are add, subtract, and OR. XXX indicates the bits 30, 29 and bit number 24 are different in these four instructions. So when the subcode is fed to the control function, then control function generates its 9 outputs as REG to LOC 0, ALU SRC 0, memory to REG 0, REG write 1, memory read 0, memory write 0, branch 0, ALU operation 1, 1, ALU op 0 is equal to 0. So only the control lines that are used are REG write and ALU OP1. Similarly, when we convert our load instructions into binary, its opcode field becomes 1111100001. So when this opcode field is fed to the control function, it generates its signals and uh, it as it generate asserted signals only for ALU SRC, memory to REG, REG write and memory read. Rest of all the signals are deserted. Similarly for store instruction, when we convert our store instruction into its binary, its opcode field is 11111000000001 sorry, and the control function generates its output depending on these opcode field are it set the ALU SRC and memory write signals as asserted and rest of the signals as deserted. Similarly for CBZ instructions, the opcode field is 10110100 and rest of our don't care. And the control signal function generates its signals REG to LOC and branch and ALUOP as asserted and rest of the signals as deserted. So now we have a single cycle implementation of most of the LEG V8 code instruction set. Let's see the unconditional branch instruction, how the basic data path and control can be extended to handle other instructions in the instruction set. The unconditional branch instruction looks like a branch instruction with a longer offset, but it is not conditional like a branch instruction. The lower order 2 bits of a branch instruction are always 0, 0. The next 26 bits of this 64-bit address comes from the 26-bit intermediate field in the instruction and then an sign extended. So we can implement a branch by storing into the program counter sum of the PC and the sign extended and shifted 26-bit offset. The addition of the control for each branch shown in this figure. An additional OR gate is used with a control signal to select the branch target PC always. This control signal called unconned branch. It asserted only when the instruction is a unconditional branch. So the figure shows that an additional OR gate at the upper right is used to control the multiplexer that chooses between the branch target and the sequential instruction following this one. One input to the OR gate is the unconditional branch control signal. Although not shown, the sign extended logic would recognize the unconditional branch opcode and sign extended the lower 26 bits for the branch instruction to form a 64-bit address to be added to the program counter. The data path we see till now are single cycle implementation. So there is a performance issue with the single cycle implementation, and that's why a single cycle implementation is not used today. Although the single cycle design will work correctly, it is too inefficient to be used in modern designs. Why this is so? Because the clock cycle must have the same length for every instruction in the single cycle design. It means the longest possible path in the processor determines the same clock cycle. This path is most likely a load instruction which uses 5 functional units in series. These functional units are instruction memory, register file, ALU, data memory, and the register file. So the overall performance of a single cycle implementation is likely to be poor since the clock cycle is too long. The penalty for using the single clock cycle design with a fixed clock cycle is significant but might be considered acceptable for this small instruction set. Historically, early computers with very simple instruction set did use this implementation technique. However, if we try to implement the floating point units or an instruction set with more complex instructions, then the single cycle design would not work well at all. Because we must assume that the clock cycle is equal to the worst case delay for all instructions. It is useless to try implementation techniques that reduce the delay of common case but do not improve the worst case cycle time. We will improve performance of our computing of our architecture by another technique that is called pipelining. Pipelining that uses a data path very similar to the single cycle data path but is much more efficient by having a much higher throughput. Pipelining improves efficiency by executing multiple instructions simultaneously.